Jai Hind. I am Madhup Agrawal, Assistant Professor in IT Department, AKGC, Ghaziabad. Today's our topic is AVL Tree Creation. So, now we will see AVL Tree Creation, how to create the AVL Tree. Before creation, first we know what is the AVL Tree. So, this is a height balance binary search tree. Height balance binary search tree means we can say this is the extension of BST. This is the extension of BST. So, why need of height balance? In some cases of the BST, when we create the BST, then just take the example. If we create, if some keys are there, just like assume 50, 60, 70, 80, 90. Just assume these are key, and we want to create the BST. So, we know in the creation of BST, this is empty BST, then there is no problem. Now, insert the 60 is greater than this one. So, we will insert this 60 into right side of this 50, and then insert the 70 is greater than 50 and also greater than 60. So, the 70 will come here in the right side, and now insert the 80 in this particular BST. 80 is greater than 50 and also greater than 60 and also greater than 70. So, 80 will come here, and after inserting 90 will also greater than all these values. So, come in the right side. Now, our created BST will be in this form. Now, see, what is the purpose of BST? Why we are creating BST? For efficient searching. Binary search tree, this search tree is used for the efficient searching in the form of log. Our target was to find the data in the log n base 2 form, worst case complexity. But in this case, if our BST in this form, this is known as skewed tree or right side skewed, so right skewed tree. In this case, our complexity will come in the form of n, So, if we are searching the data in the unbalanced BST, unbalanced means there is no connection in the right side, left side, and all the nodes are in the right side. Means roughly we can say if the tree is unbalanced, means right and left side is height unbalanced. So, our target will not achieve. Our target was in the form of log, but we are getting in the form of n complexity. So, tree must be balanced. So, how to balance the BST? So, this is the technique. AVL tree is the technique to balance the BST. So, this is a height balance BST known as AVL tree. Now, some points about the AVL tree. AVL is developed by the Anderson, Walensky and Landis. These are Russian researchers and developed in the 1962, and the AVL tree is a balanced BST if all its nodes have the balance factor belongs to the 0, 1 and -1. Balance factor. How to calculate the balance factor for each node? There is a formula. What is the formula? Balance factor is the height of the left subtree and height of the difference between height of the left subtree and height of the right subtree. So, calculate the balance factor. On the basis of these balance factor, we can say our tree is balanced or not. So, if the balance factor comes in among 0, 1 and -1, so we can say our tree is balanced. If not balanced, means other than these values, just like 2 or -2, we can say our tree is not balanced. So, there is the need of requirement of the balance the tree. Now, just take an example. This is a tree, this is a BST, and all the nodes have the balance factor among the 0, 1 or -1. So, this is a balanced tree. So, just take example, these are leaf node, and leaf node balance factor always 0. How? Height of this left subtree, left subtree is 0 and right subtree height is 0. Now, 0 minus 0 is 0. So, leaf node have the balance factor is 0 always. Now just calculate the balance factor of this particular node having value 46. Height of the left subtree is 1 and height of the right subtree is 0. So 1 minus 0, that comes 1. So balance factor of this node is 1. So our tree is balanced at this point. In this manner we can calculate the balance factor all these nodes. Just another example, we want to calculate balance factor of 65 node. So height of the left subtree 1, 2, 3. So left subtree height is 3 and right subtree height 1, 2, 3 minus 2 equal 1. So balance factor of this node is 1. In this manner we can calculate the balance factor all these node, all the node having the balance factor 0, 1 or minus 1. So our tree is balanced. So this is the AVL tree. This is balanced BST. We can say this is a AVL tree. Now in this case the balance factor of this particular node 65 comes minus 2. So our tree is unbalanced. How minus 2? So height of the left subtree, that is 1, and height of the right subtree, that is 1, 2 and 3. So 1 minus 3, that is minus 2. So our balance unbalanced. So our tree is unbalanced in this case. So there is a requirement for the balance the tree by using the method AVL methods. We will see further AVL method. So now we have seen the how to calculate the balance factor. Now just our tree is in any scenario our tree is balanced, fully balanced in this case, and we want to insert a new node, that is 50. So this is also a BST. So BST rule will follow, means the less element than a particular node comes to the left side and greater element to the particular node comes to the right subtree. So insert 50. If we insert 50 in this particular balanced tree, then 50 just compare with the root node having the value 65 and 65. Now 50 is less than 65, so comes into the left subtree, means here in this branch. Now compare there is the data, so compare 50 again with the value 30. Now 50 is greater than this particular value 30, so come in the right subtree of the 30, so comes here. Now there is also a data present, so 50 is greater than 46, so come in the right subtree of this particular. Now there is also a data 57. Now 50 is less than this particular 57, so 50 will come here. Now there is no data, so 50 will come here. Now after inserting the 50 to the left of the 57, now recalculate the balance factor. If you want to recalculate the balance factor, so balance factor of the 50 will be 0 because this is a leaf node. Now left subtree height minus right subtree, 0 minus 0, that is 0. Now the 50's parent is 57. Now calculate the balance factor of 57, that is 1. This left subtree height 1 minus right subtree height, that is 0, that is 1. So okay, there is no problem. Now calculate the balance factor of its parent. So we will calculate the balance factor in the ancestor manner. So 57's parent is 46. So we will create we will count the balance factor of this particular 46. So height of the right subtree, that is 1, and left subtree is 1 and right subtree is 1 and 2, that is 1 minus 2, that is minus 1. So okay, this height is also okay in this case. Now calculate the balance factor of this parent of 46. So height of the left subtree of the 30 is 1 and right subtree 1, 2 and 3. So 1 minus 3, that is minus 2, that is not acceptable in this case because accepted value are 0, 1 and minus 1 only. Now so we find the unbalance. So stop here. Now there is need of some technique to balance at this point. So we will say, if we find the minus 2 or 2, we will say this is the pivot point. This is pivot point. Now 30 is our pivot value. Now what to do? Now 30 is our pivot value, means the nearest ancestor of the new node, that is 50, whose balance factor has become +2 or -2 is node 30. So this is the pivot node represented by the P, this is P, and we will also identify the Q and R also. What Q? How to find the Q? What is the Q? That is the root of the pivot subtree where new node is inserted. Root of the pivot subtree. Now the pivot subtree have the two subtrees. One subtree is this one and other subtree is whole this one. Now where the new node is inserted? In which subtree is new node inserted? In the right subtree, and the root node of the right subtree, that is 46. So now this become the point Q. This become the point Q, and find the R. R is the root of the subtree of the Q where new node is inserted. Means the Q has the two subtrees. One is left and another is right. So where new node inserted? New node is this one, and new node inserted in the right subtree of the Q. So this become the R point. So first find the P, Q and R. Now, so find the P, Q and R. Now what to do? Now there is a need of AVL rotations, and these AVL rotations dependent on the situations of the P, Q and R. Now to make the tree balance, there is need of rotation known as the AVL rotation, and depending upon the which side of the pivot a node is inserted, there are 4 situations. This situation, first, this is the first situation, and we are finding the PQR. Maybe Q is left to the P and R is the left to the Q. This may be situation number 1. So LL problem, this situation. Second situation, this Q right of the P and R right of the Q. So this is a RR situation or RR problem, right problem. This may be situation also. Second situation, this is the second one. Third situation, Q left to the P and R right to the Q. So this is the left right, this is the left and then right LR problem, this type of problem. And the fourth one, this is the third situation, and now the fourth is Q right side of the P and R left side of the Q. So this become the fourth situation. So these 4 situations, on the basis of these 4 situations, different types of the rotations are required. So just depending upon the types problem, there are 4 types of required AVL rotation. Just in the LL problem, 1 rotation is required in the pivot point. In the case of LL and RR, 1 rotations are required. In the case of LR and RL, 2 rotations are required. And if the 1 rotation, then point is only pivot. We rotate at the point pivot in different direction. If the LL problem, then right rotation. If the RR problem, then left rotation. If the LR problem or RL problem, we need 2 rotations. Our first rotation goes to the point Q in both cases, and the second rotation goes to the point P, means at the pivot. Now directions, we will see the directions on the figure clearly, but here first rotation, if our situation is LR, then first rotation left rotation at the Q, and so second right rotation at the pivot. If the situation is RL, then first right rotation at the Q and second rotation left rotation at the P. Now we will see in the previous slides, just in the figure. First situation, this is LL situation. So 1 rotation is required at the P. So where to rotate? Rotate to this particular side. We can illustrate by the figure. If our tree is unbalanced in the left side, then rotate on the right side in this case. And the after rotation, after rotation this particular Q point comes after rotation, we will see further, but here we can also see the Q will come upside and this particular R and this particular P comes to the right side of the Q in this situation. After rotation at the point P, we will get this particular tree, balance tree. Now, if this situation RR situation, then one rotation is required at the P. In which direction? Our tree is inclined to the this right side. So, after rotating the left side, we will balance the tree. So, in this rotation, we will after rotation at the point P, now Q will come upside and R is here and P will go down. Down means in the left subtree of the Q in this situation. Now, in this situation, what happened? In this situation, two rotations are, in both situations, two rotations are required. First at the Q and second at the P. Just see the directions. At the Q, our tree is inclined to the right side. So, rotate at the left side, first rotation. And the second rotation at the P, in which direction? Our at the point P, our tree is inclined to the left. So, rotate the right to balance the tree. So, right rotation, second rotation perform at this point. And in this case, first rotation at Q, in which direction? Left inclined at the Q. So, right rotation is required, right rotation. And at the point P, our tree is inclined to the right. So, left rotation is required. This is second rotation and this is first rotation. This is the right direction. Okay, we will see further. Now after rotation, this is LL situation. Now, in the case of LL situation, one rotation is required at the P to the direction right side. Our whole nodes may be connected in this manner. This is the PR. What is the PR? Right subtree of the P point, and this is the QR, that is right subtree of the Q point. Now, and R may have many nodes in the downside. So, after rotation, our Q comes upside, as we see Q upside, and this branch are same in this manner, and P will come to the right, rotate here. So, this down and this PR right side of the this particular subtree, okay, and this particular node will go where? Now, this situation. So, we will see all the values in this particular subtree are less than P and greater than Q, less than P and greater than Q. Now, start from here, greater than Q means come to this particular side, right side, and less than P come this side. So, our new attachment will come here for the this particular QR. Now, QR. So, same we can see here the situation. So, QR will come to the left side, attached by changing only the pointers values, we can detach from the Q and attach into the P point, and so no problem. Now, the second situation, in this situation, right, there is one rotation required at the point P. At the point P, we will rotate to the left side. So, after rotation at this point, Q will come upside. Now, this particular branch untouched or something, and P will go down, means this will become the left subtree. So, this is P left side, no problem, attach in the same manner. Now, the tie up for the Q left side, where to attach? Now, see P, QL, all the values in this particular QL is greater than this particular P and less than Q, less than Q, less than Q and greater than P, means this particular situation here, this location. Now, we will attach QL here, we will attach QL here. So, we will get, after rotation we will get these new situations of the node. So, this is Q, P, R, this is PL and this is QL. In this manner we will attach in this situation, single rotation situation, just RR. Now, in this situation, if P, Q and R sum in this manner, this is P, this is Q and this is R. In this situation, if you connect. So, in this situation 2 rotations are required, first at the Q and second at the P, and Q right left rotation and at the P right rotation is required. So, first rotation, in the case of first rotation, so rotate at the Q, in the we will get what, get R will come upside, see here R will come upside and this branch untouched, R left side. So, this is the RR and Q will come downside, only see in this subtree, only see in this subtree. Q will come downside, means left subtree, and QL untouched. Now, the scenario for the RL in the same case as previous one, RL, this is greater than Q and less than R, greater than Q. So, this RL will come here, RL new attachment, and upside is the same attachment, this is P and this is PR. Now, we will get this particular tree, PRQ, QL, RL, this particular same after first rotation. And when we rotate the left at the point P, second rotation, then at this point R will come upside, now P right subtree and PR same. Now, this branch will be same here, same here, Q, this is QL, this is RL. Now, this particular node go where? This is less than P and greater than R, less than P. So, in this situation, this is RR. Now this is the figure. Now, this is balance. Now, our tree is BST is balanced by using AVL technique after 2 rotations. Now, the next situation is this one. This is P, Q, this is Q and this is R. In this situation 2 rotations are required, yes. First at the Q, Q left right rotation and at the P left rotation. So, after right rotation at Q, only see in this subtree, after rotation at Q, R will go upside and this particular Q left in the right subtree of the R, QR same, and this left attachment will be same at the R, RL, and this particular attachment, this is less than Q and greater than R, less than Q. So, this will come here RR and others are same. Now, this is P and this is PL. After first rotation we will get this one, and now after second rotation at P, left rotation at P, what happen? If we rotate left, R will come upside, R, and in the left subtree P will attach here, P, PL, and this particular branch untouched for R, Q, RR, and this is QR. Now, for this is greater than P and less than R, greater than P. So, this RL will attach here. Now, we will get this particular scenario same as. So, in this manner we will rotate our unbalanced tree and find the balanced one. So, we can see this by the example also. Now just take an example, just insert the following sequence of element into the AVL tree. Starting with the empty tree, the values are 71, 41, 91, 56, 60, 30, 40, 80, 50, 55. So start with the empty tree. Just now take the 71. After 71 there is empty tree, so insert the node 71. Now calculate the balance factor. Our tree is balanced or not? By looking this is balanced, but by using the balance factor of this particular node, left subtree height 0, right subtree height 0, 0 minus 0, 0 we can write here. So balance factor is in the range, so our tree is balanced. Now insert the second node 41. Now 41 is less than 71, so attachment will be the in the left subtree. So this is the 41. After inserting the 41, recalculate the balance factor. Our tree is balanced or not? So by using the balance factor, calculate the balance factor of this one. This is leaf node, so 0. Now parent of 41 is 71. So 1, left subtree height 1 minus 0, that is 1 minus 0 is 1. So our tree is balanced because balance factor is in range 0 and 1. So accept it. Now second node, insert the next node, that is 91. 91, insert 91 here. 91 is greater than 71. So insert here 91. Now recalculate the balance factor of new ancestors of new node inserted. If we indicate new node by double circle, then 91, balance factor of 91 is 0, leaf node, no problem, calculate. And this is 0 height of the left subtree minus 0 height of the 1 height of the left subtree and 1 height of the right subtree. So 1 minus 1, new value is 0, 1 minus 1, 0. So our tree is balanced now. Now insert 56. 56 is less than 71, come here, and greater than 41. So 56 will come here, attach here. Now calculate the balance factor. Balance factor of 56 is 0. Parent of 56 is 41. So balance factor of 41 is height of the left minus right, 0 minus 1, that is minus 1. Parent of the 41, height of the left 1, 2, 2, this is 2, and height of the right subtree 1, 2 minus 1, that is 1. So we will get 1, 1 and 0. So this is accepted. We will only calculate the ancestor of the newly inserted node, recalculate the balance factor of ancestor of the new inserted node. Now insert the new value 60. Now 60 is less than 71, greater than 41 and greater than 50. So inserted here. Now insert the 60, recalculate the balance factor. 60's balance factor is 0, leaf node. 56 balance factor is, this is 0 minus 1, that is 0 minus 1, minus 1, accepted. Now 41 balance factor, left subtree height 0, right subtree height 2. So balance factor is minus 2. Now minus 2, we will get the balance factor minus 2 of the node 41. So stop here, no need to calculate upside. Stop here and find the PQR. So now this become the pivot first where our tree is unbalanced, and the subtree where new node inserted, root of the subtree where new node inserted. So subtree is this one and new node is root of this subtree is 56. So this become Q, and subtree, root of the subtree where new node inserted, there is no subtree, and subtree only one node, this become R. So this is PQR. We find the PQR, and this is the situation of RR. How much rotations we required? Only one rotation, have we seen in the previous slides. At which point? At the P. At the P point, in which direction? Our tree is inclined in the right side, so rotate into the left side. One rotation at the P. So after rotation, just see only in this part. After rotation at the P, 56 will come upside and this 41 attached to the left side of 56 and 60 is untouched here. So, after rotation we will get this one, other are same 71 and 91. Now, our tree is balanced. We will see 0, 1 balance factor is accepted 0, 1 or minus 1. What is the meaning of this? 0 means right subtree height and left subtree height both are same. 1 means this particular means we can accept the difference of 1 or minus 1, means 1 height difference are accepted. So, at every node point there is no difference more than 1 height. So, okay, yes. Now, insert the new node 30. In this balance subtree, insert the new node. 30 is less than this one, less than this one, less than this one, 30 will come here. Now, recalculate balance factor of ancestor of 30, new node inserted 30. Balance factor is 1 minus 0, that is 1. Balance factor of this is 1, 2, 2 minus 1, that is 1. Balance factor of 71, 1, 2, 3, 3 minus 1 is 2. So, our tree is now unbalanced at the 71, node number 71. So, find the PQR, these become P and subtree. There are two subtree, 56 subtree, this subtree and this 91. New node is 30. So, we will consider 56 as Q and Q point 2 subtrees, this left subtree and right subtree. New node is in the left subtree. So, root of the left subtree is 41. So, we will consider PQ and now R. PQR, this is left, 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 left. How much rotation? How many rotations? 1 rotation is required at the point P. In which direction? In the direction P, right direction. So, right direction, we move at the right direction. So, in this case, if we move, then we will get 56 upside, 71, then 91, no problem. And in this branch, there is no problem, simply attach 41, 30 and this 60, this 60, this is less than 71, greater than 56, greater than 56, less than, we will also see in this manner. So, attach here. Now, our tree is balanced in this case. Now, insert the next node is 40, 40 will go where? Less than this one, less than this one, greater than this one. So, 40 will come here, 40. Now, calculate the balance factor of ancestor. Now, a balance factor of 30 is 0 minus 1, this is 2, 2 minus 0, 2 minus 0 is 2. So, our tree become unbalanced at this point. Now, this is the P, this is the Q and this become the R. This is the situation of 2 rotations. We have seen this is LR situation. 2 rotations are required. First rotation at Q, in which direction? In left direction, because our tree is inclined to the right side. And second rotation, in the second rotation is required at the P in the direction right side. So, after rotation, so only see in this scenario, in this subtree, after rotation, what we will get? After rotation, after first rotation, we will get 40 upside, 30 here and 41 here. And then second rotation, after second rotation, what happen? 40 here, 40 upside, 41 in the right side and 30 is on the left side. Others are untouched, means this is 56 and 71, 60 and this is 91. Sorry, this is 91. So, our tree become balanced in this manner. Now, insert another node 80, 50 and 55 and rotate accordingly. We can see more here. This is 60, this is 91 and this is 30 and this is 41. Now, it is balanced. Now, insert the 80. 80 is greater than and then less than. Now, recalculate the balance factor. Balance factor of this is okay, one difference is acceptable, 1 minus 2, that is minus 1, this is 1 2 2 minus 3 is minus 1, accepted, no problem. Insert the next node that is 50 less than 56 greater than this one, this become the 50. Now insert the 50 insertion node, calculate the balance factor of insertion node. This is now this is okay, this is -1, this is 1 minus 2 minus 1, this is 1 2 3 3 minus 3 0. Okay. Now insert the next node, that is 55. Where to insert? Less than 56, greater than, now this is 55. Now recalculate the balance factor, this is 0, balance factor for this -1, this is -2, left height 0 minus 2 is -2. Now unbalance at this point, this is RR situation, one rotation is required at the point here, this become P, this become Q, this become R, one rotation is right, a left rotation is required. So rotate left, after left rotation only consider this particular subtree, after left rotation as 41, we will get 50 upside, 41 here and this 55 here. Okay. Now attach all other nodes as it is, this is 40, this is 30, now this is 56, this is 71, here 60 and 91 and then 80. So our final AVL tree is this, which is the balance BST. So in this we require different rotation, by using different rotations we will get the final AVL tree, which is the balance BST. Okay, Jai Hind.